Hello students, in this video I would like to discuss about breadth first search. Breadth first search is one of the simplest algorithms for searching or traversing a graph. Given a graph G equal to V, E and a distinguished source vertex S, breadth first search systematically explores the edges of G to discover every vertex that is reachable from S. It computes the distance, that means smallest number of edges from S to each reachable vertex. It also produces a breadth first tree with root S that contains all reachable vertices. The algorithm works on both directed and undirected graphs. Breadth first search is so named because it expands the frontier between discovered and undiscovered vertices uniformly across the breadth of the frontier. That is, the algorithm discovers all the vertices at distance k from S before discovering any vertices at distance k plus 1. So breadth first search is one of the graph traversal algorithm where we give two things are input. One is graph and another is source vertex, and it finds each and every vertex which is reachable from that given source vertex. So vertex are colored during the search to indicate their state. Every vertex is initially white, grayed when it is discovered, but all adjacent vertices are not discovered, blackened when all adjacent vertices are discovered. Every vertex has one timestamp d of v which records distance from S. Distance here is number of nodes from starting vertex to the given vertex v. Pi of v records predecessor or parent of v. And this algorithm uses the data structure Q. So before going to the formal algorithm, I will try to explain the working of breadth first search with the help of an example. So here a graph is given. We must have a source vertex, and this algorithm will find all the reachable vertices from the given source vertex. So here we have a graph with 8 nodes R, S, T, U, V, W, X, Y, and we have to choose a starting vertex. Here S is selected as the starting vertex. Choose S. Color all vertices other than starting vertex as white. Initialize pi value of all vertices other than starting vertex as nil. Initialize d value of all vertices other than starting vertex as infinite. This is initialization step. The next is color S as gray. D of S equal to 0 because the distance from S to S. There is no need to go to any other nodes, so the distance is 0. Pi of S is nil. So always the parent of starting vertex in both BFS and DFS will be nil. NQS, that means put S to Q. So here D of S is given as 0, pi of S is given as nil. Next step, we have to look at the front of Q. Front of Q contains S. So here we remove S from the Q. So DQS, color S as black, color all adjacent white vertices of S to gray. So here S has two adjacent vertices R and W. Previous slide both are white, now it is colored to gray. D of R equal to D of S plus 1, D of W equal to D of S plus 1, because here we have two adjacent vertices. The distance is updated as D of R equal to 1 and D of W equal to 1. The meaning is number of nodes from S to R is 1. Pi of R is S, pi of W is also S, because I already told you it will generate a tree. So we reached R from S and also we reached W from S. So parent of W and R is S. NQ R and W, put R and W in the queue. You can put R and W in any order in the queue. Here I put alphabetically lower value first, then I put alphabetically greater value, that is W. So again we have to look at the front end of the queue. Front end of the queue is R. So DQR, R is removed from the queue. Color R as black. Color all adjacent white vertices of R to gray. That is, in the previous slide V is white. Color that to gray. d of v equal to d of r plus 1. D of r is already 1, so d of v will be 2. Pi of v equal to r because we reached v from r. Here the adjacent vertex is v, so put v in the Q. Again look at the front element in the Q. W is the front element. Next step, delete that W or DQ that W, color W as black, color all adjacent white vertices of W to gray. The previous slide T and X is white, so here we color T and X to gray. D of T equal to D of W plus 1. D of W is already 1, so D of T is 2, D of X is also 2. Pi of T and pi of X is W. NQ T comma X. So here also we can put elements T and X in any order in the Q. Here also I put alphabetically lower node to the Q, followed by alphabetically greater node. Again you have to look at the front of Q. Front of Q is V. So DQV, color V as black. Again we have to look at the adjacent vertices of V. No adjacent white vertices. So again we have to look at front end of Q. Front end of Q contain T. So DQT, color T as black. Color all adjacent white vertices of T to gray. T has two adjacent vertices, X and U. If you look at the previous slide, X is already gray. In the previous slide, U is white. That means T has only one adjacent white vertex now, that is U. Color U to gray. D of U equal to D of T plus 1. D of T is already 2, so D of U is 3. Pi of U equal to 2. NQU, put U in the Q. Again you have to look at the front end of the Q. X is at the front end. DQX, color X as black. Color all adjacent white vertices of X to gray. X has 3 adjacent vertices, T, U and Y. If you look at the previous slide, only Y is in color white, so we have to change the color of Y to gray. D of Y equal to D of X plus 1, that is 3. Pi of Y equal to X because we reached Y from X. NQY, put Y in the Q. Now front of Q is U. Remove U, color U as black. U didn't have any adjacent white vertices, so again we have to look at the front of Q. Front of Q contain Y, so DQY, color Y as black, no adjacent white vertices. Q is empty, BFS finished. So here we stop BFS when Q becomes empty. But in DFS, if any unvisited vertices are remaining in the graph, we have to apply the DFS procedure to the remaining unvisited vertices. Here, if there are any unvisited vertices after Q is empty, we will not do anything because those vertices are considered as not reachable from the source. This pi value means parent of each node. Here parent of S is nil. What's the meaning? In the output breadth first tree, S will be the root. Here parent of R and W is S. So what's the meaning? S has two children, R and W. So the purpose of pi array is to extract depth first tree. Okay, next is depth first search output. This is the input graph and these darkened edges are the discovered edges. Already I told you S is the root. From S we find R and W. W has two children X and T. X has one child Y, T has one child U. Similarly R has one child V. So these are the vertices which is reachable from S. So here in this example every vertex is reachable from source vertex. Next is classifying edges by breadth first search. In undirected graph, no back edge and no forward edges are there. For every tree edge, u comma v, we have dv equal to d of u plus 1. So if you look at the d array, which we have already computed in the example, you can see the property for tree edge. For tree edge means this blackened edge. If the edge is u comma v, we have d of v equal to d of u plus 1. For every cross edge u comma v, we have d of v equal to d of u, or d of v equal to d of u plus 1. So here we have three cross edges, xt, xu and yu. So from the earlier table you can verify this property also. These three properties are for undirected graph. Similarly, for directed graph, there is nothing called forward edges. For each edge u comma v, we have d of v equal to d of u plus 1, that is for tree edge. For every cross edge u comma v, we have d of v less than d of u plus 1. For every back edge u comma v, we have 0 less than d of v less than d of u. So you can verify these properties by applying BFS on a directed graph. Next is the pseudocode and analysis. This is the initialization step. So what's the meaning of statement 1? For every vertex u other than source vertex, you have to color it as white, initialize distance as infinite, initialize parent as nil. After that you have to color starting vertex as gray, distance as 0, parent as nil, because starting at vertex will be the root of output depth first tree. So the parent of root is always nil. Initialize q as empty. First we nqs, source vertex is put in the queue. When q is not empty, we are doing these things. Do u equal to dqqq. Element in the front is removed. For each vertex v, element of adj of u, that means for every vertex adjacent of u, if the color is white, we are doing these things. We are changing the color to gray, we are updating value of vertex to d of u plus 1, that is distance of parent plus 1, and pi of v as u. Then that particular vertex is put in the queue, and the color of dequeued node is changed to black. So this is the formal pseudocode. You can compare the example with the pseudocode. The same procedure is used in the example also. So by comparing it, you can understand it properly. So next we are moving to analysis. The operation of enqueuing and dequeuing takes O of one time, because only we are using 2 pointers, front and rear. So by constant operation we can perform enqueue and dequeue. So total time devoted to queue operation is O of v, because each vertex is enqueued to queue and dequeued from the queue only once. So if a graph contains v vertices, the total time for enqueuing and dequeuing will be O of v. Every adjacency list is scanned at most once, because here also the input to the algorithm is in the form of adjacency list. So every adjacency list is scanned at most once. Since the sum of length of adjacency list is O of v, where e is the number of edges, that is the time taken to scanning the adjacency list. So every adjacency list is scanned once, and the total length of those adjacency list is same as number of edges. So that time taken for scanning process is O of e. The overhead for initialization is O of v, because line number 1 to 4 the complexity will be O of v. Thus total running time is O of e plus v. That's all I want to share in this video. Thank you.